Alright, in this video we are talking about properties of a fluid. And after watching this video, you should be able to define what a fluid is, be able to tell me what pressure is, and then be able to use the pressure formula in terms of solving equations that involve pressure problems. So let's get right into when you talk about, and as always, the book pages are listed on the bottom, so if you're looking for another reference, pages 340 through 343 is where this information is coming from. So first question is, what is a fluid? And when I think of fluid, I actually immediately think of a liquid, and that's not exactly correct. I mean, it is correct, but it's not 100% correct, because a fluid is any substance that takes the shape of its container. Okay, that definition's pretty simple when you start thinking about it. So if I say take a wood block, for instance, so say I take a wood block and I put that wood block in this cup. The wood block does not take the shape of this cup, right? It still is a wood block. But let's say I pour some juice in this cup. The juice will certainly take the shape of the cup. Or let's say I take a balloon and I blow a balloon up with the air in my lungs, and that air will take the shape of the balloon. And so a fluid can either be a gas or a liquid. The thing it can't be is it's not a solid. Okay, so when we're talking about fluids, which is what this unit's going to be revolving around a lot, we're talking about either a gas or a liquid. And you may say to yourself, well, what is the difference between a gas and a liquid? Well, the answer to that question is basically a liquid is not compressible for the most part. So the point is that if you take, say, a syringe and fill it with water, and you try to squeeze the water with your fingers, in the syringe, the water doesn't budge an inch. And actually a lot of hydraulic lifts and stuff are a fluid in these joints, and basically the fluid is the thing that's going to push up, say, like cars or that type of thing at like car repair shops. So a liquid is not compressible, meaning it can't be squished any smaller, whereas a gas is. So you kind of think about, like, if you blow up a small balloon, you can certainly squish that gas down, or you can compress it. And so, like, if any of you have air compressors at home, basically it's pulling air from the outside into that tank, and that tank is compressed air. So a gas is compressible, a liquid is not. Well, what is pressure? Pressure, which is usually signified by a P, is the force on a surface divided by the area of the surface. Okay, and so this actually is the formula for pressure. The force on an area divided by the area, force on a surface divided by the area of the surface. And so here is the equation in all its glory. P, which stands for pressure, equals force divided by area. And typically the force is going to be in newtons, and the area will usually be in meters squared. And then pressure is measured in this thing called a Pascal, which is PA. So that's basically the rundown on what the equation is for pressure. And so basically, if I give you two of those things, you should be able to figure out the third piece, the unknown to that equation. So as I mentioned in the previous slide, pressure is measured in pascals, which is abbreviated with a PA, which is actually equal to 1 Newton meter squared, which kind of makes sense because if you go back to the formula, P equals F over A. F is going to be in newtons, and A is going to be in meters squared. And so there it is. That is 1 Pascal. Newton over meter squared. Typically a kilopascal is used, which is 1,000 times more than just a Pascal, and the reason why is because a Pascal is so small. So typically pressures will be measured in kilopascals. And I don't know if you guys knew this or not, but the air actually has weight to it, and we have about 70 miles of air over our head, and that 70 miles of air actually does push on our bodies. So our bodies are experiencing pressure, and it's squeezing in on us in all directions. And you may say to yourself, well, how come we aren't getting crushed by this air pressure? And the reason why is we actually have air pressure in our bodies, which are balancing the forces pushing on the outside of our body. One of the things that's kind of cool to look at is, like, if you ever visit Venus, Venus's air pressure, its atmospheric pressure, is about 92 times stronger than ours on Earth. So if you were to say go stand on Venus, you'd be like crushed instantly in a second, just because the air pressure is so strong. It'd be kind of like going way deep down into the bottom of the ocean, where the water pressure is extremely strong. So our atmosphere, luckily, is a little bit more friendly than, say, Venus's. And we have about 15 pounds of pressure pushing on our bodies, which is the equivalent about of 100 kilopascals. And so you can see 100 kilopascals is only 15 pounds of pressure, so a pascal is clearly a lot less than, say, a kilopascal. And I don't know how many of you guys have ever experienced the sensation of having your ears pop. Typically this occurs for me anyway if I fly in a plane. And the reason why is when you're on a plane, basically as you go higher and higher up in the atmosphere, your altitude's increasing and there is less air above you as you get higher and higher in the sky. And so because there's less air above you, the pressure is actually decreasing. And since there's a decrease in pressure, your internal pressure hasn't changed at all. And so it's actually pushing on your ears. It's really pushing everywhere, but your eardrums are relatively sensitive instruments. And so they feel that pressure, so it feels like they're popping per se. And here's a picture of basically the atmosphere. Here maybe we are, standing on Earth or standing in the water or whatever. And these little blue dots here are supposed to represent molecules. And so down here on the nearest to the Earth, there are the most air molecules. And the reason basically why is because gravity is the strongest the closer you are to Earth. As you get higher and higher up in the sky, you have, one, less air molecules, so you have less air pressure. And this is partly why, like, if you're a mountain climber, people sometimes actually bring oxygen tanks up way on the top of mountains because the air is so thin up there that when they breathe, they aren't getting enough oxygen. So sometimes people will pass out or whatever when they're, climbing a mountain. And again, here's this plane gaining altitude, and as you get higher and higher in the sky, the air pressure becomes less and less. And so here you can see at sea level, it's about 101 kilopascals, and as you get higher and higher, here's 31 kilopascals at the top of Mount Everest. So the air pressure is about a third of that of what's on the surface of the Earth, and then way up here, you're almost in outer space where there is no air pressure. Now you're entering into the vacuum of outer space. So here is a pressure problem for you guys, for you to mull over. Let me just quickly change my pen color so that it is something that actually can be seen, which is always a plus. So it says a child has a mass of 30 kilograms and is standing on both of his feet, which have a total cross-sectional area of 0.4 meters squared. What is the average pressure exerted on the ground by the child's feet? And as always, I recommend drawing your problem, just to get an idea of what you're looking at. Okay, so this is supposed to be a child. Sure, he is happy. He's standing on the ground. Okay, both feet are on the ground. And we want to know, what is the pressure exerted by both of his feet? And he has a mass of 30 kilograms. Okay? And we know that these feet down here have an area, total cross-section of area, about 0.4 meters squared. Okay? So you may want to immediately start throwing these numbers in the pressure formula, which we just talked about, P equals F over A. And that's very tempting to do, but the trick is that this 30 kilograms is a mass. It is not a force. So we need to get the force of this kid on the ground. And in order to get the force, we need to actually figure out his weight, right? We need to know his weight. What is this kid's weight? And if you remember, weight equals mass times gravity, right? Which kind of makes sense, because if this kid was in outer space, he wouldn't be pushing on the ground at all. He'd be floating, right? Because we need that gravity piece to be pulling him down. So basically, this to figure out his weight, we have to take 30 times 9.8, which is the acceleration due to gravity on Earth. And if he was standing on a different body in the solar system, this would be a different number. But basically, if you throw that in your calculator, I get a force of 294 newtons, right on the dot. So that's nice, no decimal points at all. 294 newtons. Now that I know that, the force is 294 newtons, and I know that he has a total cross-sectional area of 0.4 meters squared, now it's just basically throwing numbers in this equation. So I'm going to have 294 over 0.4, and if you do that math, I get 735 pascals of pressure. And that would be the answer to that problem. Okay. Now, it says, what would the average pressure be if the same child, balanced on 1 foot? Okay, so I am far from a good artist, which you guys will soon see. But we'll say, okay, he's doing something where he's like, I don't know, putting 1 foot in the air or something. He's still happy, of course. And the question becomes, well, what is the new pressure that he's exerting on the ground by this 1 foot? Well, the formula still is the same. P equals F over A. This kid still has a mass of 30 kilograms. Just because he put one leg in the air doesn't mean he loses mass. And the cross-sectional area is now going to be cut in half, right? Because 1 foot is no longer on the ground. So it was 0.4 meters squared. Now it's 0.2 meters squared. So that's kind of the piece here where you have to know this intuition of that. Basically, the area has been cut in half because his foot is up in the air. So the area is 0.2 meters squared. Now again, I cannot use this mass as my force. I need to use his weight, which I'm just going to pull that number from up here. This 294 newtons is still good, right? His weight hasn't changed since he put his foot in the air. So the formula is going to be, or the number is going to be 294 newtons divided by 0.2 meters squared. And if you throw that in your calculator, I get an answer of 1,470 pascals. And kind of to check our work here, if you look at this, you would imagine if he is lifting up one of his legs, the pressure would probably double because the area has essentially been cut in half, right? This is a inverse type relationship here between pressure and area. So if you decrease the area, the pressure is going to go up if the force stays the same. Okay, and that's what's exactly happened here. The force has stayed the same, the area has been cut in half, and so the pressure is going to double because 735 is half of 470. So if you were really like, on your game and you kind of had an understanding of what's going on here, you basically could take this number and double it because you won't have to do any of this stuff because you just know, well, his weight hasn't changed at all and the area has just been cut in half. All right. So that gives you hopefully an idea of a beginning in terms of understanding fluids and pressure, and we will see you guys in the next video.